Yeah. My name is Jeroen Vermeulen. I'm one of those people who make a living optimizing queries in part. Uh, so thank you for that. I feel a lot better. Uh, the unexpected vodka martini, no, espresso martini I got today before breakfast also helped. This is really a programmer talk. Is anybody here a programmer in their spare time? Some of them. How many of you know C++? Because that really helps for this one. Excellent. Okay, there will be a few people who will see a lot of stuff that they will not understand. It's a very dense language, slowly getting better. But it's a short talk, so you'll be fine. Just sit it out. Has anybody used libpqxx? A tentative hand there. Well done, sir. Proud of you. So, libpqxx is more or less the official client library or language binding if you want to talk to Postgres from C++, insofar as there is an official one. This is a long and complicated story. I know I was there. I started writing the thing about a quarter century ago. But yeah, official. It's like many other language bindings. It's built on the C language binding, but that doesn't mean you can't hear me. Oh dear. Okay, now I hear myself. Okay. You might think, oh God, it's a wrapper library on top of a C library. It's going to be slow, but I actually managed to get it faster than the C library in some cases. And because I put performance in the title, you will see some of those cases here. Oh yes, and it's under a BSD license, which is very, very liberal. So you can use this pretty much any way you like. You can even ship it to your customers as part of your product. Yes, this is a complicated slide, but trust me, when you've seen this, you basically understand everything that's going on. This is how you use libpqxx normally in your code. It's pretty simple. The only thing I did differently in the design is you have to have a transaction object. As in SQL, work is just an alias for transaction. So the way you work is your code talks to a transaction object. The transaction object talks to a connection, which talks to your database. And obviously, you create them in the opposite order, right? You create your database, then you make a connection to it, you create that connection, and boom, you're connected. Then you create a transaction that talks to the connection. And of course, once you're done with one transaction, you can open a new one on the same connection. And because we like to store data in databases, we also like to get data back. So there's a result object that can go the other way. So here's some sample code. This is almost all there is to a normal, simple libpqxx program. You include one header. You start your program. You create your connection. Once this object is created, you are connected. If that fails, you just get an exception. There's no checking whether that succeeded or anything like that. This would normally be your connection string. That's where you say where your database is, what host, what the name of the database is, your username, your password, etc. And you create your connection, so exactly like I said over there. And here's the magic. You execute some SQL, in this case, an advanced query, and you get a result object back. Right? Simple, no surprises for anyone, I think. And a result is, of course, a two-dimensional structure. So you can index that like any C++ container. You can look inside it. So this indexes a row. This indexes a field in that row. And you can convert that value, in this case, to an integer. Some C++ type on the client side of your program. Of course, you could also convert it to a string. You could convert it to a floating point value. You could convert it to many things. If it can't convert that value, it will just throw an exception. It's weakly typed. It doesn't know anything about types. So that's the basics. You don't have to remember all of this. But right now, I'll focus a bit on those result objects, which are great things. You issue a query. You get all of your data from the result data back. And then you get this result object. It's magic. The data stays in memory until you destroy the thing. And you address it like a container of containers. Super basic, just what you expect That was the design goal for libpqxx. Everything should be what I expected from C++, right? If that's your feeling, this library works. But because this is mainly a performance talk, I'm not going to tell you any more about result objects. There's something better. You can stream your query results. It doesn't work for all types of queries. This is a limitation on the back end. But you can actually tell the database to start executing a query, start streaming that data back to you, and you go through a loop where you process one row at a time. And that data for one row is only in memory for that one iteration. So if you're on a Raspberry Pi and you want to query a gigabyte of data, that's fine. You've only got one row of data in memory at a time. And this is, I've got a little asterisk here. This is faster if you're querying a lot of data. If you're not querying a lot of data, it's going to be a little bit slower, but do we care about the performance of small data? Sometimes, not usually. And I wanted to brag a little bit about why it's faster. The latency hiding means you get to process your data before all of it is in. The query may not have finished executing yet on the server. You start getting rows, you start processing them. Also makes it really hard to benchmark this feature because it's really hard to compare. In a normal program, which you would write if you were working on a C library, right? You would write a program that gets a result set, executes a query, gets all the data, starts processing. Here you start doing that beforehand. So you might be doing two things at the same time, receiving data and processing the data. I really wanted to brag about this bit. This is where I finally got faster than the C library. Turns out any Postgres front-end library needs to understand the text encoding that it gets. All of the data you receive, all the communication, almost all the communication with the backend is all in a text format. You need to parse that. So if you've got a string, for instance, you may have to scan for a closing quote, or you may need to look for a backslash that escapes a quote. And then one day, years ago, somebody discovered that there is at least one encoding, a Japanese one, in which you can have a byte that looks like a backslash or an ASCII quote in the middle of a multi-byte character. So everybody needs to be able to parse this. You're not going to do this when you use a C library. It's just too much work. You've got to parse this stuff. And with some clever inlining, thanks to C++ features, I got this to be faster than you would normally get it in C. Yay! You can also allocate a bit less memory. And these are the two things that you normally have to avoid, right? When you want to speed up your code, 30 years ago, everybody would say, find a faster algorithm. Now, all you need to do really is look for I/O and such that you can save. Do less waiting for disks and network communication, and allocate fewer chunks of memory. Now, in C++, if you're handling strings, you're allocating memory all the time. You're copying a string, you might think you're copying basically a pointer and incrementing a counter or something. That's not how C++ strings work. They copy data all the time, all over the place. But if you're using query streaming in libpqxx, you can use string view, which is really just a modern C++ equivalent to pointer length. So you can convert the string that you got from the database to a string view, which is not a conversion, it's just, here's your pointer. And I'd like to show you an example. Again, it's not that complicated. Everything happens in this line. Does everybody who knows C++ recognize this loop syntax, though? It's relatively modern, yeah? I see a few nods, good. That's syntax that was introduced in 2014, I think. So for loop, auto, which means compiler, you figure out what the types here are. I want to query an ID and a name from this here. So it corresponds pretty nicely to the SQL data. transaction.stream, and I pass what column types I want in my result. So there's no more calling the library to convert a result to your value. It just does that for you. And you do this once for every iteration. Here I do some intense processing with that data. After every iteration, that data is gone. It's actually in a buffer that gets reused every iteration. This goes back to my point about not allocating a lot of memory. So any questions about this? Because feel free to interrupt, right? No? I hope some people are, good. Yes. Aha. Nothing detects types. You say what type you want it to be. So if you've got a column of decimals and you query it and you say, no, I want these to be doubles, which please don't do that for money. That's stupid and even illegal. But if you wanted to do that, no worries. If it looks enough like a double, you can say, I want this as a double. That does mean if you've got that one weird value that doesn't convert, yeah, boom. In fact, what I am not showing you is if you also want to support nulls, for instance, in your data, you'd better use standard optional or something like that, something that's allowed to be null. Otherwise, it will go kaboom. You're asking me to convert a null to an integer, and there's no such thing. Sorry, Oracle. So I'm racing through this really quickly. Good.
Well, I know you say you cannot quantify faster, but surely you've done tests.
Yes.
Do you have an idea of what is faster? And also the second question, you said faster for, or rather faster not for small data sets.
Right. It all depends. I ran a really quick benchmark yesterday where I saved a quarter of the time on a million super simple rows. But it depends on your hardware, obviously. Depends on the latencies involved relative between your CPU, your network, what have you. And it depends also on how much work you're doing with the data client side, because you save time by doing useful work while the server is sending you the next row of data. So really, really hard to quantify, and I want to keep it vague so that if you're interested, you'll benchmark it for yourself. That's the ultimate test. So yeah, racing through this, apart from the questions, but I really enjoy those. Going the other way, you want to insert your data. And that's something we don't talk about as much. I've seen plenty of code just do this in a loop. Just do an insert. I'm also highlighting another little libpqxx feature that every library has, basically, which is you can pass parameters to a query. Insert value $1, and $1 is a name that you've got in a loop or something. This is incredibly inefficient because what was the first thing I said to avoid in high-performance code? It's waiting for other things, right? I/O and such. So if you're sending a query and waiting for the result every single time, that's terrible. I've seen code also, and I've seen this recently in production, that just concatenates a whole bunch of these tuples. So you insert a batch of, say, 200 rows into your database at once. I don't like that much. It's fine for lower volume. But higher volume, it's fine like this. And so there's streaming the other way as well. Sort of on my way to this presentation, I realized I need to give this a better API, but you can create a stream object that goes the other way, that streams data into a table. There's some relatively modern C++ syntax here. You've got a named constructor. You say, give me a stream2 from the stream2 class, construct it, call the constructor called table, and you tell it, here's my transaction, here's my table, here's a list of columns. And you can then start feeding data into that. And that works internally. It works a lot like streaming the other way. It all uses the PostgreSQL copy command, which I think is an extension, is not in standard C++. So that all just lets libpqxx do all the work, just sending and receiving text. And so you call this a bunch of times. Write values on your stream. If you've got more columns that you want to stream, you just do name, comma, ID, comma, salary, whatever. Super simple, but you've got to remember to tell it when you're done because this all gets buffered. Right? If you don't tell it when you're done, everything gets hugely confused. And then something I don't usually show in read-only examples, but you're also supposed to commit your transaction. If you've ever dealt with people, I get a lot of bug reports, and some of them are really, really, really basic. And you end up looking for the weirdest stuff. You end up going into the Postgres code. You end up looking at standards. You end up looking at POSIX networking documents. And in the end, somebody forgot to commit their transaction. Ah, good. Yes. For my what, sorry? Yep. Yep. Copy to standard out and copy from standard in, respectively. Because I could get all those speed benefits. I'd love to discuss this later, absolutely. I mean, yeah, I may sound dismissive, but I really enjoy the questions. And again, I'm racing through this because I wasted so much time dealing with, computers and all that stuff. So, oh. I would say the song festivals are the worst waste. My girlfriend made me watch the songs, and absolutely Croatia. Nobody else came close. We had to fast forward through all the songs because she is. You've met her. I think you've met her as well in Belgium or in Prague. Ah, okay. This is the last slide. Just wanted to show you where to get all this. I will put the slides up there, obviously. And this is the time for the overall questions that I never answered. Good. Memory limitations. Postgres has a few memory limitations. And so a lot of stuff inside Postgres is actually limited to, say, a gigabyte. So, and even then, I don't really run into those. Because if you're querying a 3 gigabyte result set, you've got people waiting, you're just not doing it, right? I have run week-long transactions. This is not something you should ever, ever, ever do on a database that has multiple users. There was a time when I didn't know that, and I was more or less in charge of a database, fairly large one. Had a fun career there optimizing queries until finally we got more memory, and and I'm so good at it, I just optimized something to the point where I'm suggesting to my bosses, we should have less memory. So I still have a job optimizing queries. But yeah, I've seen other databases buckle or explode after 10, 20 seconds of a transaction. This is about the worst thing I've done on Postgres, and you're fine. libpqxx also, so far, yeah. Any other questions? I was hoping for that question. Thank you. So to repeat the question, which I have been neglecting to do, I'm sorry. Does this mean that you have to run everything in a transaction with begin and commit? No, you don't. That's just the C++ side design. So you always have to use a transaction object, but there is a class called non-transaction. And that's where you're running an auto commit. But in terms of how it looks to your code, it's always a transaction. You're just specifying, I don't want a transaction on the database. You can use that for schema changes, for example. And that also means you get to swap out different kinds of transactions. So if you want a different isolation level, it's a compile time change. You just change your transaction type. There's a transaction type that's extra robust, so that if you lose your connection at just the wrong time during your commit, which sometimes happens, right? You lose your connection, you've got an error, you've got no idea whether your changes have been committed or not. You can't even retry them because they might have completed. And you can't just go and check and say, well, is the data there? Because that update might still be running on the server by the time you reconnect. So there is one transaction type that protects you from that sort of thing. So wide range of choice. Pagination. Pagination is your problem. I just say don't do limit offset. Unfortunately, a lot of people don't realize that, but yeah, no, you can use cursors. I don't do it for you. There is cursor support. Done? Yeah? Thank you all very much for listening.
Well, let's get started. Do you all hear me? Good. Well then, I'll be talking about Neon and the issues that we hit when we were trying to build a serverless Postgres or a Postgres without a permanent local data storage. I'm Matthias from the Meent. I've been hacking on Postgres since September 2020. Mostly, I should not be clicking that so much. Mostly on bug fixes, but recently some larger features as well. Hired by Neon in 21 to work on their Postgres fork, and now I work basically full-time on Postgres development. If you're looking for nice features in Postgres 17, which is releasing in September, I basically helped with the new explain feature called serialize, where you can also test how much data your query actually produces. Before you couldn't see that. And it also was skipping some things like toast. It's going to be also including that data, which is really nice if you have like 90% of your data in the toast tables. Before it would complete in 10 milliseconds, now it will take seconds. Which is good because now it's actually accurate for your actual query. So, yeah. That's enough about me. Now about Neon. We built what we say is a developer-friendly PostgreSQL software as a service, an open source version of Aurora. We have a similar architecture, some small differences. But one of the main ones is that we can instantly clone the database. This means that you can create a copy of your database, run your migrations against the database and check, hey, I added a not null constraint, but it actually failed. That's bad, but at least it wasn't on the production database where it would have locked the table for some time and shut down whatever work. And now it hasn't even actually done anything useful, apart from saying, hey, there is an actual null value in my not null constraint. Other nice features that we have with our system is scale to zero. AWS Aurora does have an older version of their serverless offering, which also scales to zero, but their latest version doesn't do that. And as far as we know, there are no other PostgreSQL vendors out there who scale their databases to 0 and scale them up the moment you need them. We have implemented this quite well, which means you start from the first connection, you can get it up within 500 milliseconds, and we scale it down when it's been idle. You don't pay for no resource usage. And autoscaling of memory and CPU based on usage, you don't pay for what you don't use. That's my employer. The basic architecture is you have Postgres compute node with some safekeepers which get the wall, the changelog basically of what your Postgres modifies for short-term local storage. Then it's modified by a page server, which also serves read and write requests from Postgres. And eventually, all the persistence is guaranteed by an object storage like S3. But if you're self-hosting, it could be anything, Minio, Google Cloud Storage. If you have put in the effort to make a block to use object storage from them, basically anything. As I mentioned earlier, now we scale to 0, which means this Postgres shuts down and is thrown away. A normal Postgres instance can have many, many, many gigabytes of data. Might not be normal for you, but there are many people who have tens, hundreds, and thousands of gigabytes of data in there. If you want to start a Postgres in the reported 500 milliseconds, you can't shove terabytes of data in there in milliseconds. We don't have the compute resources for that, nor the network bandwidth. So we have to do something there which hides this latency from getting all the resources to the Postgres instance. So that's what I'm going to be talking about. How did we solve most of those issues, and how are we still increasing the size of a Postgres instance that we can host? First is the disk dependency, then how do we ship the data? How can we support replication, physical and logical? Some issues that we hit with statistics. SLRUs are basically the systems that maintain transaction states and things that are related to transactions, things that need to be really, really, really low latency within Postgres. And then extensions, because you may not always think about this, but extensions can be huge. Things like PLV8, if you're using it, it's 400 megabytes of disk space being used by that extension alone. Not everyone uses it, so it's oftentimes wasted disk space if no one is actually using it. So, yeah. So, Postgres has a huge dependency on the disk. Data lives in various folders. We have persistence data about persistence, for instance, the wall, the transaction log, things, metadata in the stats. There are various binaries, extension files. But the main data in Postgres is persisted through wall. That means that all changes are appended into a single file and are then synced to disk. Once the changes are synced to disk, it is considered persisted. In long-term persistence, you can't really keep those changes in the series in the wall, because that would mean that every time you shut down your server and start it up again, you have to replay all the changes. So, as one usually does, you store it on the disk in normal files, so that you can also remove the older change logs. And for that, the Storage Manager API is used to actually write out the changes that were buffered in memory. But the issue is that WAL doesn't always contain all changes. For instance, the command ID to say, hey, it was this command which changed the this row version, is not contained in the transaction log, in the write-ahead log, because write-ahead log is only used to recover from a crash. And the command ID is only useful within a transaction. So if you crash, the transaction is invalid, so your command ID is useless. So it isn't logged. Visibility hint bits as well. The changes in the wall are, it doesn't contain the visibility hint bits because the wall is also used for physical replicas. And if I'm on a physical replica, I may have started a transaction which doesn't need to see newer transactions as committed, which were already committed on the primary. If visibility hint bits were locked, then I would have to be really precise about where and when I start and stop my transactions on the replica, because otherwise my hint bits get updated and then suddenly I think, hey, my transaction is visible, but it can't be visible because I started my transaction way earlier than that transaction, that other transaction committed. So you get some issues there, and then suddenly your replica starts falling behind on replaying wall, and that's not something you want. But there are many other such issues. And because of our architecture, we don't actually have local files in our Postgres, or not normal data files. But if we only have the changes in our, if we only get the changes from wall, then we have to get our changes somewhere else. So we modified our wall format. We replaced the storage manager so that we can get our pages from the from our page server, and we store all data changes as mentioned through wall exclusively. We send our wall to 3 safekeepers. They essentially behave as if they were 3 Postgres replicas, except they don't actually serve queries and they don't actually store any data other than the change log, using a PAX's quorum of 3. After which this wall is processed and indexed by page server, persisted to S3, and whenever a Postgres needs a change, or actually needs to read a page, it requests that page from the page server, and the page server will then get whatever changes are needed from the wall, which it indexed, and then replay those changes for specifically that page. Which has a great benefit because we requested the latest version, but we can request any version of the page, which is how we get those, this earlier mentioned, instant database clones. And at any point in time, because we know at which page was modified how at which point in time. So we can also know, hey, this page should have looked like this at this point in time. And for every page in the server. Yes. So we can shard this data at any level now, but we do have issues because we don't have the data locally. We have to request it across the network, which adds I/O latency. And we don't have any persistent unlocked tables because unlocked tables don't have any change logs, which means we don't know what happens there. So when you shut down a server, all unlocked relations are empty. There are some changes, so we also needed changes for correctness and good performance. The command ID was critical because otherwise you would get the Halloween problem of seeing tuples multiple times if the page was flushed from memory before the transaction committed. Visibility and free space map logging was also critical. This doesn't happen in normal Postgres, but we have to write out the dirty visibility map and free space map into WAL because otherwise we lose a lot of the benefits of the free space map and the visibility map. For instance, index scans index-only scans require that the visibility map is the all visible int bit is set for a page before it can actually use its optimization of only returning the tuples that are interesting and not hitting the heap pages. But if the visibility map doesn't know which pages are all visible, you have to go into the heap every time, and the index-only scan isn't an index-only scan anymore. Other issues, the streaming replication or physical replication. Normal Postgres applies all changes. We don't want to do that because we have limited resources available, we have limited network bandwidth available, and we already have all pages. We can already query pages at every point in time, so we just skip all changes that we don't have in cache. So we will request the correct version later. We don't care. The wall will already be replaced by page server if we need to, and if we don't have it in cache, then probably no one needed it. So, yeah. Other replication slots. The state of replication slots is not stored in wall because it contains up to which point the replication slot it has replayed the changes from wall. So if you store it in the wall, up to what point the wall has been replayed, you get a chicken and egg problem of, hey, I changed, hey, I'm up to date now, which is 5 bytes of, let's say 50 bytes of changes. I'm not up to date anymore because I put 50 bytes of changes into the wall. This is actually not a huge problem because usually it's based on commit times, offsets rather than actual offsets themselves, which means the repeated write-out isn't that huge of an issue, but we did implement it like that because we didn't have a good way to do it otherwise in a quick way because we needed replication done basically yesterday by that point. But yeah, same with logical replication. The state store for logical replication is not designed for ephemeral use. You can't just delete it and just think everything is going to be fine. Snapshots and mappings, they are critical in the working of a logical replication. But if you lose all the data every time your Postgres restarts, you're going to be in for a bad time. So the quick solution was wall logging the files and include them in the base backup when you load the base backup to start a new Postgres node. But it's a lot of wall, which increases commit latency for normal workloads, which also create wall. And it's a feedback loop, as I mentioned. The replication creates new wall that needs to be replayed, which needs confirmations, which creates new wall, which needs to be replayed, which, and so on. But the future solution, which we've been working on, will use another distributed system, which has confirmations as well, but which is not in the wall, which means that we can update them separately without generating more changes in Postgres, which increase commit latency. But it might increase sync latency for replication subsystems, which we think is going to be fine, but it's a work in progress. Another item, cumulative statistic systems and things like pgstat statements create ephemeral files, which are usually flushed to disk when your Postgres server shuts down and then recovered into memory whenever your Postgres server starts, unless it has crashed, in which case the data is just dropped. We crash all the time, as in not unexpectedly, but we lose all this data every time, so it considers it's crashed every time. And we don't have so we lose the file. And in principle, it isn't bad per se. Postgres is built to handle this, but a lot of the information in these files is used as a guide post for auto vacuum to start working on new tables and old tables and that kind of stuff. Which means that if we don't have these files, these statistics files, AutoVacuum doesn't know anything about what to do on the tables. Which is kind of bad because AutoVacuum is a critical component in keeping Postgres kind of clean. So we're still working on this. But yeah, eventually we'll have a similar solution like the previous one. We aren't quite sure yet how to correctly do this. But yeah, this is one of the items that we have open for, hey, this is actually an issue that we have to solve. Next item, SLUs. Previously, we included them in the base backup, basically the base image that we use to start up a Postgres instance quite quickly. It's quite easy to have it in the base backup, and it can be quite cheap as well, but some customers have huge SLUs. And that can significantly increase the cold start latency because some of them can be up to half a gigabyte, but some of them can be up to 4 gigabytes. And downloading 4.5 gigabytes, say, just to start your Postgres instance, that's not a great deal if your network is only 5 gigabits per second. A quick calculation takes about a second then, in an optimal case. So now what we do is we download the segments of the SRU on demand, which means there's lower cold start latency. But in some hot code, we can require a download. Usually this isn't too much of an issue because we aggressively start downloading these SLRUs whenever we start a node. So it may be cold at the start, but if after a few seconds it will be warm enough for no one to care anymore. And usually people don't require the full SLRUs at the start of their node. So we consider this to be a good trade-off. A good time to first query versus a time to fully optimized. Yeah, that was a trade-off. So, as mentioned, extensions can also be quite huge. We had a Docker image we have a Docker image per Postgres version, and all extensions loaded in one image was up to 1.2 gigabytes, which is nice. Get everything into one image, and it's easy to add new extensions, but it gets to be a large image, and each user wants their own extension. For instance, if I wanted to, say, install the community version or the non-free version of Timescale with all its nice features, that can become quite an issue because that can be quite huge. And I can't actually do that as Neon because the license of that is fairly restrictive in what you can do with it. As in, sure, you can do a lot with it, but then you also have to open source basically all of your infrastructure, which is not something we can do as a normal company. Sure, we do want to open source a lot, and we do open source a lot, but everything is a bit too, open sourcing everything is a bit too much to ask. So yeah, everyone wants their own extension, and it's a large image. So what we decided on is doing hot loading of extensions as well. We still have a Docker image per Postgres version, and we still have a lot of extensions bundled, but newer extensions are loaded on demand. We do have additional hooks now in the load path. So if Postgres asks for a file, starts loading an extension and checks, hey, does this file exist? We do have a hook there that if it does not exist, and we know it should exist, that we ask our sidecar to load the extension data. And it prioritizes the loading of that file. There are some issues though. Postgres has shared preload libraries, which are files which are loaded before Postgres even starts accepting connections. So those extensions must be loaded before Postgres starts. No questions asked, must be. Same with session preload libraries. Before a session starts to accept any commands, it must have those files. So what our sidecar does, it aggressively preloads the extensions which are in those settings for shared preload, session preload, and local preload. And after that, it starts loading the rest as time goes on to make sure that whenever someone starts to need it afterwards, it is actually available as soon as possible, rather than at exactly the start of the first query, which would move the next query way later. Well, I hope I entertained you. If there are any questions, then I would happily answer. Yes.
You said the architecture was similar to that of Aurora.
Yes.
How much is really known about Aurora's architecture?
Actually, quite a lot. There is at least one, I know of one presentation which goes in quite a lot of detail. There are some changes in Aurora though, which we don't do. Aurora has basically 6 replica safekeepers, if you will, and page servers. We only have 3 safekeepers and 1 page server per Postgres project. Postgres instance, basically. We've recently been working on getting that to 2 to have at least a hot page server when one of them fails, or connection failure, or that kind of stuff. But that is one significant change. The other significant change between Aurora and our fork is that Aurora does modify how the wall, the wall or the changelog is written. They have every backend write their own messages to every of the page and safekeepers, while we use Postgres' own wall formats insofar that we can, of course, and are therefore mostly compatible still with normal Postgres and the normal operations of most extensions. Yes. Does that answer your question?
Absolutely.
Okay. Yes.
For the scale down to 0,
Yes.
First of all, is it an enterprise feature or no?
It is not. That is how we support our free tier.
Okay, cool.
You can try it out yourself.
Yeah, exactly.
Yes.
And I'm very curious about the idle. Like, how do you handle the idle? When you do it, or is it configurable? Like, the connections, the number of connections.
We basically check for every connection how long they've been idle and how long it's been since a new connection did anything. By default, and for free tier users, that's like 5 minutes, which is quite reasonable actually. Other user, if you're on a more premium tier, then you can disable it or set it to higher or lower settings, I think. I am not entirely up to date with that because I'm not on the product team.
And then I have a question on the startup time.
Yes.
Is that only the connection, so from no connection to unconnected?
It's basically from us receiving the first connection to the user sending a query.
Sending a query, okay.
Well, having the first query getting executed, because there still needs to be some I/O for getting the
So that's
yes.
Right.
Well, yeah. Does it not? No, it does not. Does this not? Okay, yeah. My it went into sleep mode, and this still works, so that's nice. But yeah, the page server is effectively a cache onto S3 because S3 has a high latency, a rather high latency, and you can't really have the 100 millisecond latency of S3 for every I/O that you do in Postgres. So what we do is we have a cache and we have our own indexes to make sure that the Postgres I/O is still quite efficient. Yeah, does that answer your question? Good. Yeah. That's a really good question. The answer is we don't shut down while AutoVacuum is running. That's the only solution, and it's only a half solution because AutoVacuum doesn't run all the time when it actually should be running in 5 minutes, say, because AutoVacuum assumes that it will be able to run in some time as well, which is not the case in our case because we shut down. So yeah, it isn't great. Yes. What we basically do is we put the authentication that is registered in Postgres also in our own servers, so that we can actually accept connections and make and validate that the connections are connecting with correct authentication. And once the server is online, we just forward the connections to the Postgres server so that it can handle the authentication once it's online. We do have a fairly heavyweight proxy which also does things like WebSocket forwarding, so that you can connect to the Postgres server using WebSockets, or HTTP forwarding, which means that you can use HTTP requests to do full transactions per request. It's a fairly diverse proxy which does a lot of things, including Postgres forwarding. Yeah. Any other questions? Well then.